morning, everyone. So, as discussed in the last lecture, we have seen the definition of a first axiom space, second axiom space, and separable space. Okay, and some of the statements we have seen, right? And after that, we will first again revise whatever we have seen very fastly. So, I think from the compact spaces we have started. Okay, and after compact space we have seen finite intersection property. Then we have seen some of the theorems related to compact space. Then we have a definition of homeomorphism. After that we have seen separation and connection. Okay, what is a definition of separation and what is a definition of a connectedness? Okay, both are completely opposite. And what is a meaning of separation? That means we should have a two non-empty disjoint sets such that their union gives the set itself and neither of them contains the limit points of other. And connectedness is exactly opposite of them. And what is a very important theorem related to them is said to be any set or any space is said to be connected if it has no proper subset which is both open and closed. And if you are getting any proper subset which is both open and closed, then you can say that that set is a separated set. Then we have seen some of the theorems related to connectedness and separation. Okay, if C is a connected set, then we have seen what is okay, we are provided with x2 is any t space, and we have to find out that whether C bar is also connected if C is connected. Okay, and we have proved that theorem that if C is connected, C bar, that is closure of this set, is also connected. And if E is toe connected, then E star is toe star connected. Okay, and we have seen what is cofinity space. Okay, x2 is cofinity space, then it is connectedness or not. We have to discuss this, and we have discussed the assumption that that cofinity, we have proved this result with the help of a contradiction. Cofinity space is not a connected. Sorry, cofinity space is a connected space. Even in the very similar way, we have to prove it is co-countable space is also connected. And very important theorem, that is X is connected if there exists no proper subset of X which is both open and closed. And if there exists at least one proper subset which is both open and closed, then it is called a separated. And we have seen how to find out the limit points and how to find out whether any set is a connected or not. I have given you in detail example that how to find out whether set is connected or separated. Just you have to verify all the 5 conditions. A and B both are non-empty, disjoint, the union gives X. These 3 are easy to verify. Just you have to think on the point that whether neither of them contains the limit points of other. That means you have to check A intersection D of B is empty, or another. And the next condition you have to check is a B intersection with D of A is empty. So if you verify these 2 conditions, the result okay. Okay. After that, we have seen what is completely regular space. For completely regular space, we should have one closed set F which does not contain the point X. Then we have to define a mapping F. If there exists a mapping F which is a continuous mapping from X to closed interval 0, 1 such that F maps uh, the element X to 0 and F maps the closed set F to a singleton 1. Okay. Then we have seen every completely regular space is a regular space. Then we have seen what is a definition of a T3 half space. T3 half space is T1 plus completely regular. In the very similar way, we have discussed in detail what is your normal space, what is T4. T4 space is nothing but normal plus T1, right? In the very similar way, we have a T3 space. What is T3 space? Regular plus T1, and we have seen that there is no relation between regular and normal. But if any space is a regular plus T1 or regular plus normal, that is every T3 space is a regular, and every T4 space is a regular, and every compact T2 space is a normal as well as it is a regular space. Okay, so in this way, very there are so many relations to find out what is a relation between completely regular, normal, regular, and all. And if you are provided every normal plus regular space is a completely regular space. And very important theorem related to this one, which we have seen from the starting of T naught, T1, and all. Those theorems are being any space, whatever may be the resultant, T naught, T1, T2, T3 half. Okay, just now we have seen for T3 half is a hereditary and topological property. And after that, we have seen every compact T2 space is a completely regular. Compact plus T2 space is a completely regular space. This theorem I have told you to prove with the help of two statements, that is compact T2 space is normal as well as regular, and just now we have proved normal plus regular is completely regular. And after that we have seen the definition of a first exam space. So what is a first exam space? First condition is for every element of x we should have a family of a open set Bn of x. Okay, first we should find out the family of a open set. Next, every x is a member of a Bn of x for all element for all n. Next condition is uh, for we should able to find out the open set G such that x belongs to that Bn of x, and Bn of x is contained in your G. And if you are able to find out such a open set, then the result holds. And we have seen whether discrete T space is a usual T space is a FAS. Okay, Fourth space is not a FAS. Okay, so if fourth space is not a FAS, it is not satisfying the first axiom of countability. In the very similar way, you can prove that your co-countable and cofinity space both are not a FAS. And after that, we have seen the definition, theorems related to FAS, that is hereditary and topological properties. And what is the definition of second axiom space? In short, definition of first axiom space is like we should have a countable local base. Okay, and you know very well about the what is local base. But here in the second axiom space, we should have a countable base at every point. Okay, just like we have discussed for a usual topology, we have a base. How to define a base is, suppose I have for a usual topology, we know that every set or every open set in our topology, or to be a member of a two, it can be in the form of a open interval. So if it is in the form of a open interval, so I have selected this base as a open interval AB such that A and B are the members of a rational number, right? So in this way we have proved that a B is a base, and itself now we have to prove that whether usual topology is a second axiom space. And one more remark, we have seen that if X is uncountable set, then discrete T space is not a SS. Okay, if X is uncountable, then discrete T space is not a SS. But we have seen this is a FS. Okay, discrete T space is FAS. I can classify this as, these are FAS, properties of SS, these are SS. So you can write here discrete T space is FAS, but it is not a SS. And the consideration X to be an uncountable set. Okay, because small hint for this one is, if X is uncountable, how you are able to find out the countable base? And next we have proved every second axiom space is a first axiom space. Then definition of a Lindelof space. As I told you, the Lindelof space and compact spaces are very similar, because in the compact space we have to find out for every open cover we find a finite subcover. But for Lindelof space, what is the result? For every open cover, there exists a countable subcover. Okay. So in this way, we can say that every compact space is Lindelof space. Whatever the theorems we have seen related to compact space are going to satisfy this condition. That is, every compact space is a Lindelof space, because finite can be countable, but countable का property finite के लिए true नहीं होगा, right? Every compact space is a Lindelof space. And again, if compact space is satisfying closed hereditary property, those who remember, we have studied that closed subset of a compact space is a compact space, or we can say that being a compact space is a closed heredity. So in the very similar way, being a Lindelof space is a closed hereditary property. Okay, the reverse one, I will give you one example whether this condition is true in the reverse way. That is, every Lindelof space is a compact space or not. Every Lindelof space need not be compact space. Okay, the example for this one I will give that X is one countably infinite set. X is one countably infinite set, and 2 is a discrete topology defined on it. Okay, so you have to find out that it is a Lindelof space, but it is not a compact space. Why this will not be a compact space? Because you can see here, suppose I have selected these all the singleton X as a open cover, but what will be the finite subcover for this one? We cannot find out the finite subcover. Why this is so? Your X is uncountably finite. Huh? So you cannot find out the finite subcover, but you can find out the countable subcover, because X itself is given to us countably infinite. So you can say that there does not exist a finite subcover, but we know that there exists a countable subcover. This itself will work as a countable subcover, because every element of two is an element of power set of X. So every subset of X is a element of 2. That's why we can say every singleton X is a member of 2, and itself will work as an open cover, and we cannot find out the finite subcover. Again, I will give you one more example that every Lindelof space need not be second axiom space. Okay, so in that case, the example is cofinity space. What is a cofinity space? Cofinity space is a compact space. We have proved this, no? Cofinity space is a compact space. So every compact space is a Lindelof space. Finite, hai na? Finite can be countable, because every open cover has a finite subcover, and here you should have a countable subcover. But it is not a SAS, since cofinity space, Ford space, and co-countable space all are not a FAS. Sorry, not a FAS. So hence it is not a SAS. So these cofinity space, co-countable, as well as Ford space, we have written that these are not a FAS. So अगर वो FAS ही नहीं है तो obviously they will not be SAS. So whatever the theorems we are seeing now, we should have some connection with the old theorem. Because if you know compact space, then only you can come to Lindelof space. That is, every open cover has a finite subcover, but here we have every open cover has a countable subcover. And just now we have seen that every Ford space Ford space, cofinity space and co-countable T space are not a FS. अगर वो FS नहीं है तो obviously SS नहीं होंगे. Why this is so? Because we have proved one theorem related to SAS and FS. What is the theorem we have proved is every SAS is a FS. So very similar statement we can say that contrapositive of this one is not a FS will not be SAS. Right now? Not a FS will not be a SAS. So not a FAS means what? Obviously it will not be FAS. First axiom of countability, second axiom of countability. Then we have seen the definition of a separable space. So what is a separable space? Separable space is the thing that there should exist a countable dense subset in X. There should exist a countable dense subset in X. And I will show you one more topology we have defined. Many spaces we have proved to be a topological spaces like cofinite, co-countable, Ford space. Then we have proved discrete, indiscrete. Then we have proved with the help of X is equal to set of natural number an is equal to some 1, 2, 3 and so on up to n, or it starts from n plus 1 and so on. There is one more topology is defined which is important here. This is P exclusion topology. P exclusion T space. What is P exclusion T space? Which is actually we are going to define this on a X is uncountable set. If X is uncountable set, we have to define this P exclusive topology. So how the topology is defined? 2 is equals to the set X union with a subset of X such that P is not a member of that set. Exclusive, the name itself suggests that P exclusive means what? The point P should not be a member of that open set G. Right? So now here to be a member of 2, there are two possibilities. Either you should be whole set X itself, or it should be the condition that this is an open set which does not contain the point P. In the very similar way, we have one more topology, that is P inclusive or P inclusion topology, in which the definition is defined as the set X union with the subset of X, rather open subset of X, which contains the point X. Very similarly, we have defined the ray topology, that is, it is of the form A to infinity. That means it is just like A, starting from A to infinity. Then being a separable space is a topological property, and then every every second countable space is a separable space. But converse need not be true. Every SAS is a separable space, but the converse is not true. Converse is true only in the condition that it is a metric space. That means I will write down one statement that a metric space is a separable if and only if it is SAS. And separable space is not a hereditary. So this is what are very important for you, because closed hereditary we have seen, hereditary we have seen, but not a hereditary. So separable space is not a hereditary property. And one more condition, that every separable space need not be Lindelof space. You can give the example of either P exclusive or P inclusive. The exclusive topology is a Lindelof space, but it is not a separable. Now here you can see that separable space is not a hereditary, but it is open hereditary. Closed hereditary नहीं है, hereditary भी नहीं है. So what we can say about the separable space? Open subspace. That means you have to take open subset of your separable space. Open subspace of separable space is separable. Even every Lindelof space is not a separable. In this way, very easily you can cover the syllabus if you are going to have all the relation at a single page or one or more pages, and just try to write down and cover the syllabus. Okay, thank you.